Hello everyone. Today we will study our new chapter that is solution in detail. So let's start with the disclaimer slide which says the images used in our slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the image. Let's move to the index slide. So these are some major topics which we will going to study. Concentration of solution, vapor pressure, Raoult's law, ideal solutions, non-ideal solutions, Azeotropes, Henry's law, Raoult's law as a special case of Henry's law, colligative properties, determination of molecular mass from osmotic pressure, abnormal molar masses, Van 't Hoff factor, significant of Van 't Hoff factor, and modified expressions of colligative properties. So let's start. Some concentration of solution terms. So solution is a homogeneous mixture of two or more substances on molecular level. The substances forming the solution are called components of the solution, that is solute and solvent. Various methods for expressing concentration of the solution are as follows. First one is molality, represented by small m. It is the number of moles of solute dissolved in 1000 gram of solvent. So its formula is given by the molality is equals to number of moles of solute divided by the weight of solvent in kg. Unit is important here. Second term is molarity, represented by capital M. It is the number of solute present in 1 liter of the solution. And its expression is given by molarity equals to number of moles of solute divided by the volume of solution in liter. The relationship between the molality and molarity is given by this formula, which is M molality multiplied by the D density divided by 1 plus the fraction of molality and molar mass of solute multiple and 1000. So we have given here that M2 is molar mass of solute and D is the density of the solution. And M is, we know that molality of solution we represent by M. Relationship between molarity and density is given by this equation. So density into 10 into percent by weight of solute divided by molar mass of solute is equal to the molarity. Third is mole fraction denoted by kappa, and this is a type of X symbol. So it is the ratio of the number of moles of one component, either solute or solvent, to the total number of moles of solute and solvent present in the solution. You can say moles of solution. So mole fraction of solute in the solution is moles of solute divided by the total moles of the solution, that is moles of solute plus moles of solvent. Mole fraction of solvent is moles of solvent divided by total moles of solution. Sum of mole fractions is always equal to 1 in a solution. So mole fraction of solute plus mole fraction of solvent is always equal to 1. The relationship between molarity and mole fraction is given by this equation, that is M1, where M1 is the molar mass of solvent, M2 is the molar mass of solute, and D is density. So mole fraction is given by molarity into molar mass of solvent divided by the molarity multiplied by the difference between the molar masses of solute and solvent plus its density or density of solution. This is the expression or relation between molarity and mole fraction. Move to our next term, that is percent by weight or mass percent. So it is amount of solute present in 100 gram of solution. We can show it in this way, that the percent by weight is equals to weight of the solute divided by weight of solution multiplied by 100, as we are talking about the percentage. Fifth term is percentage by volume. So the volume of solute in milliliter present in 100 milliliter of the solution is called volume percent. Okay, so here L will come volume percent. So percentage by volume is volume of solute in ml divided by volume of solution in ml multiplied by 100. Sixth term is mass by volume percentage. It is the mass of the solute dissolved in 100 ml of the solution. So mass by volume percentage is given by mass of solute divided by the total volume of solution in milliliter multiplied by 100, as we are talking about percentage. Seventh term is parts per million or ppm. When the amount of solute in grams is present in 1 million milliliter per ml of solution, the concentration of solution is expressed in parts per billion. So you can say that ppm concentration is equals to mass of solute multiplied by the 10 to the power 6, or you can say 1 million, divided by mass per volume of solution given in gram per milliliter. Eighth term is normality. It is the number of gram equivalents of substance dissolved per liter of the solution. So normality is given by number of gram equivalent of solute divided by volume of solution in liter, where gram equivalence is defined as weight of solute per equivalent weight of solute. Okay. Ninth term is solubility. So the maximum amount of a solute that can be dissolved in a given amount of solvent at a given temperature is termed as solubility at that temperature. So solubility of a gas in liquid depends upon temperature and pressure. Solubility is directly related to the temperature and pressure of the solution. The quantitative relation between pressure and solubility of a gas in a solvent is given by Henry. So this phenomena is given by Henry vapor pressure. So we will study now about vapor pressure. So the pressure exerted by the vapor molecules above liquid surfaces which are in equilibrium with it at a given temperature is called vapor pressure. So this is the definition of vapor pressure. And what are the factors which affect the vapor pressure? So vapor pressure gets affected by the following factor. Number one, purity of the liquid. So pure liquid always has a vapor pressure higher than its solution. So if we have any kind of pure liquid, no mixture, then it has a vapor pressure higher than its solution. And second factor is nature of liquid. So liquid which have weak intermolecular forces are volatile because their particles can easily, escape from the surface of the liquid and have greater vapor pressure. So their vapor pressure is greater. So nature of liquid will also affect the vapor pressure. Third factor is temperature. The vapor pressure of a liquid increases with the increase in temperature. This is because on increasing temperature, the kinetic energy of molecules increases, results into the fact that more molecules of the liquid can go into vapor phase due to the higher kinetic energy. Fourth factor is effect of adding solute. So when a liquid contains a solute, some of the solvent molecules are replaced by the solute particles on the liquid surface, and therefore the available surface area for the escape of the solvent molecules decreases, hence their vapor pressure will decrease. Due to the less available area on the surface of liquid for escape, the rate of evaporation and the rate of condensation both decreases, because evaporation depends on the available area of the liquid or surface area of the liquid. The vapor pressure of liquid in solution is known as its partial vapor pressure, and it is less than the vapor pressure of pure liquid at same temperature. If P0 be the vapor pressure of pure liquid and Ps be that of liquid in solution, then lowering of vapor pressure of liquid is equal to P0 minus Ps. So therefore we can say that relative lowering in vapor pressure is given by this formula, which is P naught minus Ps divided by P naught. So this is all about vapor pressure. Now we study about the Raoult's law. So Raoult's law for the solutions of liquids in liquid state, the partial vapor pressure of each component of solution is directly proportional to the mole fraction of that component present in the solution. In the formula, we can say that P of A component, that is pressure of A component, equals to the multiple of mole fraction of A and the vapor pressure of A component, or pure vapor pressure. And for the B component also, we can say that the vapor pressure for the B component is equal to the multiple of mole fraction of B component and the partial vapor pressure of B component. And A and B are volatile solute and solvent respectively. It is mentioned here. And PA naught and PB naught are vapor pressure of A and B in their pure state. So if XA and XB, or these and this, are the mole fraction of components A and B respectively in the vapor phase, then PA equals to mole fraction of A into P of total, that is total vapor pressure of the solution, or PB equals to mole fraction of B into total vapor pressure of the solution. Raoult's law for the solutions of solids in liquids, that is for non-volatile solutes, is given by this equation, that is the pressure of solution is equals to mole fraction of solvent multiplied by the P naught, or vapor pressure of pure solvent. There are some limitations of Raoult's law. First is, it is applicable only to very dilute solutions. If the solution is very dilute, we can apply the Raoult's law on that. Second is, it is applicable only to the solutions containing non-volatile and non-electrolytic solutes. So the solutions which are non-volatile and non-electrolytic and which exist as a single molecule, the Raoult's law is applicable to them only. Okay, only is important. Third is, it is not applicable to solutes which dissociate or associate in the particular solution. So like ionic compound, or these kind of solutes which in the on dissolving in the solution dissociate or associate, the Raoult's law will not applicable to that kind of solution. Now we study about ideal solutions. The solutions which obey Raoult's law over all ranges of concentration and temperature are called ideal solutions. For ideal solutions, del H mix, that which is enthalpy of mixing to form the solution, is equals to 0, and del V mix, that is volume of mixing to the solution, is also equal to 0. So both these terms, that is enthalpy of mixing and volume of mixing of solution, is 0 for any solution which is an ideal solution. For such solutions, solute-solute and solvent-solvent interactions is equivalent to solute-solvent interactions. Solution of N-hexane and N-heptane, benzene and toluene falls in this category. So we can consider them as an ideal solution. Practically, no solution is ideal. So if we talk about practicality, practically no solution is ideal. The graphical representation of ideal solutions is given here. So if any solution is showing this graph between their vapor pressure and mole fraction, that means that is an ideal solution. So this is the graph in which on this axis, vertical axis, we have vapor pressure. On horizontal axis, we have mole fraction. And the mole fraction of A component is going from this to this direction, and the mole fraction of B component is going in opposite direction, right? And this is the line representation for the total vapor pressure of the solution in terms of the vapor pressure of A component and the mole fraction of their of the components, right? So this is graphical representation of ideal solution. The solutions, non-ideal solutions. Now we see that what are non-ideal solutions. The solutions which shows deviation from Raoult's law and are called non-ideal solutions. So they do not obey the Raoult law. They show deviation from Raoult law. And for such solution, the delta H mix and the delta V mix both are not equal to 0. They are either positive, they are either negative, they are not 0. So first, the non-ideal solution showing positive deviation. So they show deviation from Raoult's law, either positive or the negative. The non-ideal solutions showing positive deviation when the observed partial pressure is more than the expected by Raoult's law. So if we calculate according to Raoult's law, whatever the Weber pressure will come, and the observed partial pressure which is we are observing is more than the expected, then the positive deviation is observed, right? For how can we determine? So for such a deviation, the vapor pressure of a component is greater than their multiple of mole fraction and vapor pressure in the pure state, right? Similarly, for the B component, if the B component is present, and hence the total vapor pressure of the solution will also be greater than the sum of multiple of mole fractions of a mole fraction and vapor pressure in pure state of both the component, right? So for such solutions, the del H mix and del V mix is positive, greater than 0. These are usually obtained by mixing of polar liquids with non-polar ones. So when the polar liquids dissolve with the non-polar ones, we get the non-ideal solutions which show positive deviation. And the example for these type of solutions are cyclohexane and ethanol, H2O and ethanol, right? This is a graphical representation here of the solution showing positive deviation. So if a solution is showing positive deviation, so this graph will be observed by this graph will be given by that particular solution. Same like in the vertical vapor pressure, in the horizontal mole fraction, and for a component it is the mole fraction is increasing in this direction, and other for the other component is just decreasing in this direction. And this is the total vapor pressure line here, showing here, this arrow. So this is the total vapor pressure line, and this is the partial vapor pressure P1 and P2 for both the components. So this is a graphical representation of a solution showing positive deviation. So when the observed partial vapor pressure is less than the expected by Raoult's law, then negative deviation is observed. So non-ideal solution don't obey Raoult's law, but either they deviate positively or negatively. So positively, we have seen now for the negative deviation observation, the partial vapor pressure is less than that of expected by Raoult's law. And for such solutions, the del H mix is less than 0 and del V mix is also less than 0. For example, chloroform and acetone solution. And this is a graphical representation of the solution showing negative deviation. For a solution showing negative deviation, the vapor pressure of a component is always less than the multiple of mole fraction and vapor pressure of pure component. And similarly for any other component present in the solution, and hence the total vapor pressure of solution will be less than the sum of multiple of mole fraction and vapor pressure of the pure components. Okay, so this is all about the solution which non-ideal solution which show negative deviation. Azeotropes. So what are azeotropes? Mixture of liquids that boils at a constant temperature and distills over without any change in the composition are called azeotropes. Azeotropes are of two types. First is minimum boiling, second is maximum boiling. So minimum boiling azeotropes are formed by those liquids pairs which show positive deviation from ideal behavior. So in the minimum boiling azeotropes, the solution show the positive deviation from ideal behavior. Such azeotropes have boiling points lower than either of the components. Okay, so the boiling points is observed as lower than the either of components. Like examples for such an azeotropes are ethanol in water, ether acetone, and water methanol. Second kind of azeotropes are maximum boiling azeotropes. These are formed by those liquid pairs which show negative deviation from the ideal behavior, and such azeotropes have boiling points higher than either of the components. And their example is water, which is 20.22 by mass, and hydrochloric acid, acetone chloroform, and water nitric acid. So these are some examples for maximum boiling azeotropes. Let's move to our next topic, which is Henry's law. So, Henry's law states that at constant temperature, the solubility of a gas in liquid is directly proportional to the partial pressure of the gas present above the surface of the liquid or solution. So, solubility and the partial pressure relation is given by Henry's. And in other words, we can also say the partial pressure of gas in vapor phase is proportional to mole fraction of gas in the solution. Okay. And we can write it in terms or that the vapor pressure is directly proportional to the mole fraction of the gas, and we can introduce a constant here, kh, represented by kh and known as Henry's law constant. So p equals to kh mole fraction. Higher the value of kh at a given pressure, the lower is the solubility of a gas in a solution. So there is a relation between the kh value and the solubility of a gas. They are inversely related. If higher the kh, then lower the solubility, and vice versa. Right? So Raoult's law as a special case of Henry's law. So how they both are related. According to Raoult's law, the vapor pressure of a volatile component in a given solution is given by Pi equals to cup mole fraction and the vapor pressure in the pure form multiple. In the solution of a gas in a liquid, one of components is so volatile that it exists as a gas, and its partial pressure is directly proportional to its mole fraction, right? As we studied in Henry's law in the solution, and this is stated by Henry's law as that P is equals to KH mole fraction, right? So if we compare the equations for Raoult's law and Henry's law, it can be seen that partial pressure of the volatile component or gas is directly proportional to its mole fraction of the solution. You can see this equation given by Henry's and this equation given by Raoult's, that every term is same other than this pi naught and the kh value, right? So we can say that the partial pressure of the volatile component is directly proportional to the mole fraction in the solution, right? So only the proportionality constant kh differs from pi naught, as I said. Thus Raoult's law become a special case of Henry's law because we find that they both are related, so in which kh becomes equal to pi naught, right? Because this is the only thing which is differing. Other terms are same in both the equations given by Raoult's and Henry's, right? So hence the kh becomes equal to pi, and this case is become the Raoult's law special case of Henry's, right? So let's move to next topic, that is colligative properties. So let's see what are colligative properties. The properties which depend only on the number of solute particles, irrespective of their nature, relative to the total number of particles present in the solution, as colligative properties. Example, relative lowering of vapor pressure, depression in freezing point, elevation in boiling point, and osmotic pressure. So, for different solutions of same molar concentration of different known electrolyte solutes, the colligative properties have same value for all. And for different molar concentration of same solute, the colligative property has greater value for more concentrated solution. So when we have the same molar concentration but different non-electrolyte solutes, the colligative property will be having the same values for all the solutions. But if we have different molar concentration and same solute, then the colligative property has greater value for the solution which is more concentrated. For solutions of different solutes having same percent strength, now new term, that if we have different solutes but their percent strength is same, the colligative property has higher value for the solute having least molecular weight. There are four types of colligative properties as given below. So first is a relative lowering of vapor pressure. So addition of non-volatile solute leads to the lowering of vapor pressure. So if we add any non-volatile solute in a solution, their vapor pressure will decreases. So P naught minus P divided by the P naught is equals to the mole fraction of the solute. Or we can write the mole fraction of solute as mole fraction of a component, moles of one component divided by moles of other component. And for dilute solution, the NB is very less than Na. That's why in the denominator for mole fraction, the total moles will come. But here we are ignoring the moles of B because they are very very less than the moles of. And P naught minus P upon P naught is relative lowering of vapor pressure, and NB is the moles of solute, and Na is moles of solvent, and P naught is vapor pressure of pure solvent, right? Then relationship between molecular mass and relative lowering of vapor pressure can be given as MB, or molecular mass equals to WB, mass of solute, and MA, molecular weight of solvent, divided by WA, which is mass of solvent, multiplied by the relative lowering of vapor pressure, right? This is the direct relationship between molecular mass and the relative lowering of vapor pressure. So, second is elevation and boiling point, represented by del TB. As the vapor pressure of a solution is decreased due to the presence of a non-volatile solute, the solution boils at a higher temperature as compared to the pure solvent. Thus, the boiling point of solution is higher than the boiling point of pure solvent. It is observed, right? And for dilute solutions, the del TB, elevation and boiling point, is equals to Kb multiplied by molality. Del TB we can also write as TB minus TB naught, where TB equals to boiling point of the solution and TB naught equal to boiling point of pure solvent. And Kb is given as M of A, that is the molecular weight of the solvent, multiplied by R, gas constant, into boiling point of pure solvent ka whole square, divided by 1000 into del Hp, where R is gas constant, del Hp is latent heat of vaporization, and Kb is the ebulios, ebullioscopic constant or molar elevation constant. So Kb depends on the only on the solvent. So this is important. Kb depends only on the solvent. In the solvent, solute, and solution, Kb only depends on solvent. Okay. Determination of molecular mass from elevation and boiling point. So we can find the relationship between molar mass and the elevation and boiling point given by this formula. That is the molar mass equals to Kb multiplied by W of B, that is weight of the solute, into 1000 upon del TB, elevation in boiling point, multiplied by WA, weight of the solvent. Depression freezing point, so represented by del TF. When a non-volatile solute is added to a solvent, the freezing point of the solution is always lower than that of pure solvent. Okay, so for the dilute solutions, del TF is given by Kf multiplied by molality, and del TF we can write as TF naught minus TF, where TF naught is the freezing point of pure solvent and TF is the freezing point of solution. And Kf here is the cryoscopic constant or molar depression constant. Okay, molar depression constant. And Kf can be written as mRTF node whole square upon 1000 into del HF, where del HF is the latent heat of fusion and other terms are same as we have seen for Kb, right? Okay, now determination of molecular mass from depression and freezing point. So the relationship between molar mass and depression and freezing point is given as molar mass of solute equals to Kf into Wb into 1000 upon del Tf into Wa. Every term is same as for, as we have seen in elevation and freezing point. And fourth is the osmosis and osmotic pressure. So, spontaneous flow of solvent molecules through a semi-permeable membrane from a pure solvent to the solution or from a dilute solution to concentrated solution is termed as osmosis. Right? So, osmosis is related to the flow of solvent, flow of fluid. The external pressure which must be applied on the solution in order to stop the flow of solvent into the solution through semi-permeable membrane is termed as osmotic pressure. And it is given by N by V R T, represented by pi, and N by V can be written as C, which is molar concentration, into R into T. So N here is moles of solute, C is the molar concentration, V is volume of the solution in liter, R is gas constant, and T is temperature in Kelvin units. Okay, so determination of molecular mass from osmotic pressure. So if we have given the osmotic pressure, how can we calculate the molecular mass? So the relationship between osmotic pressure and molar mass is molar mass of solute is equals to weight of solute into R into T divided by pi, which is osmotic pressure, into V, that is volume. Two solutions having same osmotic pressure at same temperature are termed as isotonic solutions. And when two solutions are being compared, the solution with osmotic pressure with higher osmotic pressure is termed as hypertonic, and the solution with lower osmotic pressure is termed as hypotonic. So hypertonic and hypotonic are two different solutions depending on their the magnitude or the value of osmotic pressure, higher or lower, higher hypertonic, lower hypotonic. Yeah, okay. Now, abnormal molar masses. So, molar masses that are either lower or higher than the expected or normal values are called abnormal molar masses. And in the normal, day-to-day life, we also use the abnormal word when something unusual happens. So, when we are expecting or something or normally, which has a simple value, normal value, but the coming value or the molar mass is coming is either higher or lower than that, then they are called as abnormal molar masses. Association of molecules leads to decrease in the number of particles in the solution, resulting in decrease in the value of colligative properties. Everything is related. So if the molecules get associated, right, and this rate is decreased, then the number of particle will get decreased in the solution, and then the value of colligative property will also decrease. While in case of dissociation, if we see the dissociation, then the number of particle increases because they are dissociating, right? And when this happens when the substance is an electrolyte, and in this case the colligative property will increase accordingly. Now, Van 't Hoff factor, represented by I. So in 1880, Van 't Hoff introduced a factor I, known as Van 't Hoff factor, to account for the extent of dissociation or association. So, how much dissociation or how much association is happening? This we can, tell by using the Van 't Hoff factor. And this factor I is defined as in various ways, like number of particles after association or dissociation divided by the number of particles before association or dissociation, or normal molecular mass divided by abnormal molecular mass, or the observed value of colligative properties divided by calculated value of colligative properties. So these are various ways we can calculate the extent of dissociation or association using the Van 't Hoff factor. Okay. Now, significance of Van 't Hoff factor. So, quantitatively, the extent to which a solute is being associated or dissociated can be expressed by Van 't Hoff factor as the definition of Van 't Hoff factor. And for dissociation, the I, that is Van 't Hoff factor, is greater than 1. That while for association, the Van 't Hoff factor is less than 1, either 0 or negative. And degree of dissociation is given by alpha. So alpha is defined as Van 't Hoff factor minus 1 upon n minus 1, where n is the number of particles after dissociation. After dissociation of an electrolyte or a substance, how much particles ions will form? It is defined by n, and I we know it is a Van 't Hoff factor, so degree of dissociation will be I minus 1 divided by n minus 1. And degree of association, also denoted by alpha, is I minus 1 upon n minus 1. N is same that the number of particles after association. Okay, so these are the equations or relations by which we can find out the degree of association or dissociation in terms of Van 't Hoff factor and the number of particles after association and dissociation respectively. Okay, let's move to the next topic, which is modified expression of colligative properties. So, relative lowering of vapor pressure is given by P naught minus P upon P naught equals to I, that is Van 't Hoff factor, times moles of solute divided by the total moles in the solution, or you can say that mole fraction, right? So, here NB is equal to N, and NB plus NA is equivalent to capital N. So elevation and boiling point ΔTB is given by I Van 't Hoff factor multiplied by Kb multiplied by M. M is molality. Third one, depression freezing point. So ΔTF is Van 't Hoff factor into Kf into M. M is molality. And osmotic pressure we can write as pi equals to ICRT. So we can we have modified the expressions of colligative properties for 4 of them, and they are as follows, right? Okay, so now we are at our summary slide. So it contains whatever we have covered. So concentration refers to the amount of solute present in a given quantity of solvent or the solution. Raoult's law states that partial vapor pressure of each component in a solution is equal to vapor pressure of pure component multiplied by its mole fraction in the solution. We have studied this. An ideal solution is the one that follows Raoult's law throughout the entire range of concentrations, and non-ideal solutions do not follow Raoult's law due to the difference in intermolecular interactions. Henry's law states that the amount of gas that dissolves in a liquid at a given temperature is proportional to the partial pressure of that gas above the liquid. Then we study about the colligative properties, which is depending on the number of solute particles present in a solution and not on their identity. And the last we study about the Van 't Hoff factor represented by M, I, and it is a measure of effect of solute on colligative properties. So these are all the major definitions or the informations, and we have studied all these things today in this lecture. Okay, thank you.